Welcome back. This video is a complete guide to recursion in Python, one of the most powerful and often misunderstood tools in a programmer's toolkit. We'll start with the fundamentals, work through divide and conquer, backtracking, memoization and tail recursion, and finish with practical patterns you'll use every day. Let's go. A function is recursive when it calls itself, but not just blindly. It calls itself with a smaller or simpler version of the original problem, and it keeps doing so until it reaches a base case, a problem so trivial it can be answered directly without another call. Beat. 3 laws govern every correct recursive algorithm. First, there must be a base case, a termination condition that requires no further recursion. Second, the algorithm must change its state to move toward that base case with every call, usually by shrinking n, shortening a string, or consuming a list. Third, it must call itself. Violate any of these 3 laws, and your function either returns the wrong answer or crashes with a Stack Overflow. Beat. The classic first example is countdown. The iterative version uses a while loop, straightforward. The recursive version instead says, if n is 0 or less, print, go, and stop. That's the base case. Otherwise, print n, and call countdown, _rec, n-1, moving closer to 0 each time. Watch the 2 traces produce identical output. Beat. The most important mental model for working with recursion is this: trust the recursion. When you're writing countdown _rec n, assume that countdown _rec n-1 already works correctly. Your only responsibility is handling the current value of n. This leap of faith is what separates programmers who struggle with recursion from those who find it natural. Beat. The call tree diagram makes the execution order concrete. Each call prints its own n, then invokes the next frame. The base case fires at the bottom, and control returns back up the chain. Each arrow in the diagram represents a return. Beat. Recursion versus iteration is a trade-off. Recursion is often dramatically cleaner, especially on trees and graphs, where the structure of the data mirrors the structure of the recursive calls. But each recursive call adds a stack frame, and the call overhead is real. We'll learn exactly how to manage that throughout this video. Every time a function is called in Python, the interpreter creates a stack frame, a block of memory holding that call's local variables, parameters, a return address pointing back to the caller, and any pending operations waiting for the result. All these frames are stacked on top of each other. Click Let's Trace Factorial 5. The call to factorial 5 creates a frame, n equals 5, pending operation, 5 times whatever comes back. That frame calls factorial 4, which creates another frame, n equals 4, pending 4 times. This chain continues until factorial 1 hits the base case and returns 1. Then the returns cascade back upward. 1 becomes 2, becomes 6, becomes 24, becomes 120. Click the stack diagram visualizes this perfectly. Factorial 1, at the bottom, returning to factorial 2, returning to factorial 3, and so on, all the way up to main receiving 24. Click each frame in that stack contains the local variable n, the return address back to the previous frame, and the pending multiplication that's waiting for the recursive result. Click Here's the critical warning. Python's default recursion limit is 1000 frames. If your input causes more than roughly 950 recursive calls, leave a buffer for Python's own stack. You'll hit a recursion error. A linked list of 10,000 nodes, a balanced BST of 10,000 nodes, both exceed the default limit. sys.set recursion limit can raise it, but each frame costs a few kilobytes for its stack memory. Setting it to 1,000,000 frames is asking for an out-of-memory crash. We'll see safer alternatives later. Next, good recursive design comes down to 2 questions. What is the simplest possible input that you can answer without another recursive call? And how do you express the solution to a larger input in terms of a solution to a smaller input? Click Pattern 1 is linear recursion, reducing by 1 each call. Sum_list takes a list, and if it's empty returns 0. That's the base case. Otherwise, the answer is the first element plus the sum of the rest. Each call peels off 1 element, so the depth is on. Beat. Pattern 2 is binary recursion, having the problem each call. Binary_sum splits the list at the midpoint, sums each half recursively, and adds the results. Depth drops to O log n. This is the foundation of divide and conquer. Beat. Pattern 3 is tree recursion, making 2 or more independent recursive calls. Count _paths on an m by n grid. If either dimension is 1, there's exactly 1 path. Otherwise, the number of paths equals paths from the row above, plus paths from the column to the left, 2 independent subproblems. Beat. Pattern 4 is multiple base cases. The Euclidean GCD algorithm has 2 base cases. If b is 0, return a. If a is 0, return b. The recursive step, GCDB, a mod b, always reduces because a mod b is strictly less than b, so the second argument shrinks every call. Beat. Click Pattern 5 is the accumulator pattern, tail recursive style. Factorial_ACC passes a running product forward as a second parameter. At the base case, the accumulator already holds the final answer. No pending multiplication at any call site. The result moves forward, not backward. This is the pattern that enables tail call optimization in languages that support it. Beat. Click the design checklist to memorize. Identify the base case. What input needs no further work? Verify every branch moves toward it. N-1 is smaller than n. Identify how to combine recursive results, head plus tail, left plus right, and verify the combination is logically correct. Next. Fibonacci is the canonical example of why naive recursion can be catastrophically slow, and how a single decorator can fix it. Click fib_naive n has two base cases. Return n for n less than or equal to 1. Otherwise return fib_naive n1 plus fib_naive n2. Clean, correct, and brutally slow. Fib_naive 40 requires roughly 1.3 billion recursive calls because it recomputes the same subproblems over and over. Beat. Look at the recursion tree for fib5. The nodes marked with a recycling symbol fib3, fib2 are computed multiple times. At fib40, fib2 is computed over 100 million times. This is the overlapping subproblems property, and it's the signal that memoization will help enormously. Beat. Click the fix. Add at LRU_cache, max size equals none, above fib_memo. Now Python stores every result the first time it's computed. The second call to fib3 finds the answer in the cache in 01. Total calls to compute fib, 100, just 200. Execution, instant. Fib 100 has 21 digits, no problem. Beat. If you need to avoid recursion entirely, bottom-up dynamic programming fills a DP array from index 2 upward, each entry computed from the 2 before it. ON time ON space, no recursion depth concern. Beat. Click. If you need O1 space 2, the space-optimized iterative version tracks only the last two values, with variables a and b, updating them each iteration. Beat. Click. And if you need the nth Fibonacci for astronomically large n, matrix exponentiation computes it in O log n time. The identity, the nth Fibonacci, equals the top right entry of the nth power of the matrix, 1110, reduces to repeated squaring, having the matrix size each step. 12 multiplications to reach fib, 70. Beat. The performance table is striking. Naive O2_n, memoized ON, space optimized ON time O1, space, matrix O log n. Same correct output, wildly different performance. Choose by your constraints. Next. Strings and lists are naturally recursive structures. A string is either empty, the base case, or a first character followed by a shorter string. This structural match makes recursive solutions feel like they write themselves. Click reverse_str illustrates this perfectly. Base case is a string of length 0 or 1, which is already reversed. Otherwise, return reverse_str, sewn, the reversal of the tail, concatenated with 0, the head. Each call handles one character, and trusts recursion to handle the rest. Beat. Click palindrome checking is even more elegant. If the string has 0 or 1 characters, it's trivially a palindrome. If the first and last characters don't match, it's not. Otherwise, check whether the inner substring, stripping both ends, is a palindrome. ON time, ON stack depth. Beat. Click. Flattening a nested list uses tree recursion over the list's own structure. For each item, if it's a list, recurse into it and extend the result. If it's a leaf, append it directly. This handles arbitrary nesting depth with the same code. Note, in production, this still uses call stack depth proportional to nesting depth. We'll see the generator alternative for very deep nesting later. Beat. Recursive binary search shows how recursion maps cleanly onto divide and conquer. If low exceeds high, the target isn't present, return -1. Compute mid, compare with target, and recurse into the appropriate half. Each call halves the search space, O log n depth. The diagram traces the search for value 9 through 3 calls. Beat. The fastPower function achieves O log n using the key identity, x to the n equals x to the n 42 squared. That means we only need one recursive call for even exponents, not two. The depth halves each time. 1024 calls naive, just 10 calls with squaring. The table makes this concrete for powers of 2. Next. Divide and conquer is the most powerful application of tree recursion. Split the problem into independent subproblems, recursively solve each, and combine the results. The key word is independent. The subproblems don't overlap, which distinguishes divide and conquer from dynamic programming. Click merge sort is the textbook example. If the array has one element, it's already sorted base case. Otherwise, split at the midpoint, recursively sort left and right, then merge the two sorted halves. The merge step walks two pointers across the sorted halves, always picking the smaller element. Beat. The Tower of Hanoi is the purest example of tree recursion. To move n disks from peg A to peg C, using peg B, move the top n-1 disks from A to B, move the large disk from A to C, then move n-1 disks from B to C. The recurrence is T of n equals 2 Tn1 plus 1. It solves to O, 2 caret n. For 3 disks, 7 moves. For 64 disks, over 18 quintillion. This is provably optimal. You cannot do it with fewer moves. Beat. The Hanoi recursion tree for n equals 3 shows the structure. The top level call spawns 2 Hanoi 2 calls and 1 direct disk move. Each Hanoi 2 spawns 2 Hanoi 1 calls. Total disk moves, 7. Notice the branching factor of 2 per level. That's exactly where the 2 caret n comes from. B-click. The master theorem gives us a systematic way to solve any divide and conquer recurrence of the form Tn equals A times Tn slash B plus f of n. Merge sort. A equals 2, B equals 2, f of n equals On. The combined cost matches n caret log 2, 2 equals n, so we multiply by log n, giving On log n. Binary search. A equals 1, B equals 2, f of n equals O1. Combined cost less than n caret log 2, 1, which is n equals 1. Both are O1, so multiply by log n, O log n. The table summarizes the key cases. Beat. The divide and conquer maximum subarray problem shows the pattern beyond sorting. Find the max crossing subarray that spans the midpoint, the combine step. Recurse left, recurse right. Take the max of all 3. On log n. For a problem that also has an On Cadon's greedy solution, an important comparison. Backtracking is a systematic approach to exhaustive search. Build candidate solutions incrementally, one choice at a time, and abandon any partial solution the moment you know it can't lead to a valid complete solution. That abandonment is the prune step, and it's what makes backtracking dramatically faster than brute force enumeration. Click the general template is always the same structure. It's worth memorizing. The backtrack function takes the current state. First, check the base case. If the current state is a complete solution, record it and return. Otherwise, iterate over all candidate choices. For each choice, check if it's valid. If not, skip it. That's the prune. If valid, make the choice. Modify state. Recurse with the new state. Then undo the choice and restore state. The undo step is what backtracking actually refers to. Beat-click. Permutations. Path holds the current partial permutation. Remaining holds the unused elements. Base case. Remaining is empty. We've placed all elements. Save a snapshot of path. Otherwise, try each element in remaining. Append it to path. Recurse with that element removed. Then, pop it back off. The pop is the backtrack. 6 calls, 6 results for 1, 2, 3. Beat. Power set. All subsets. Every partial path is itself a valid subset, so we record it immediately at the start of each call. Then we extend it by trying each element from start onward, recurse, pop. The start index prevents duplicate subsets by ensuring we never take an element we've already passed. 8 subsets for 3 elements, 2 to the power of 3. Beaks click n queens is the classic constraint satisfaction backtracking problem. We place 1 queen per row, and for each column choice we check 3 constraints. No other queen in the same column. No other queen on the positive diagonal. Row minus call constant. No other queen on the negative diagonal. Row plus call constant. Each constraint is a set, O1 lookup. Failed constraints immediately prune the branch. Beats classic tet. The pruning power table says everything. For n equals 8, without pruning we'd evaluate 16 million board states. With pruning, 2057. For n equals 12, down from 8.9 trillion to 854,000. Pruning reduces the search space by orders of magnitude. The effectiveness of backtracking hinges entirely on the quality of your pruning condition. Next, let's apply the backtracking template to 3 more classic problems: combination sum, Sudoku, and word search in a grid. Each demonstrates a different flavor of constraint and pruning. Click Combination Sum. Find all combinations of candidates that sum to a target, where each candidate may be reused. The key insight: sort the candidates first. In the loop, the moment candidates exceeds the remaining amount, every subsequent candidate is also too large, so we break immediately. This one-line prune can cut most of the search tree. Notice we recurse with index I rather than I plus 1, allowing the same element to be picked again. Beat. Click Sudoku Solver. We scan the board for the first empty cell marked with a dot. We try digits 1 through 9. For each digit, is underscore valid checks the 3 Sudoku constraints, no duplicate in the same row, column, or 3x3 box, in one compound condition. If valid, place the digit recurse. If the recursive call returns true, we've found a complete solution. Propagate true back up. If no digit works, return false, triggering backtracking in the caller. Beat. Click word search in a grid. Start DFS from every cell whose character matches the first letter. At each step, check bounds. Check the current cell matches the expected character. Then mark the current cell with a sentinel hash to prevent revisiting it within the same path. After all 4 directions are explored, restore the cell. That's the backtrack. If we reach an index matching the full word length, we've found the word. Beat. These 3 problems cover the main combinatorial shapes, unlimited use items, summing to a target, constraint propagation on a grid, and path existence with revisit prevention. The backtracking template is the same in all 3, only the validity function changes. Mutual recursion occurs when function A calls function B, and function B calls function A. They rely on each other, forming a cycle of calls. It's less common than direct recursion, but it arises naturally in certain problem domains. Click. The classic toy example is _even. N returns true if n is 0, otherwise calls is _odd, n1. Is _odd n returns false if n is 0, otherwise calls is _even n1. The 2 functions alternate. Each call reduces n by 1, so they terminate. This is ON and only educational. Real code uses n%2. Beat. Click. Where mutual recursion earns its keep is in recursive descent parsers. The parser class handles arithmetic expressions through 3 mutually recursive methods. Parse_expr handles addition and subtraction, calling parse_term for its operands. Parse_term handles multiplication and division, calling parse_factor. Parse_factor handles numbers and parenthesized subexpressions, and for parentheses, it calls parse_expr again. The 3 functions form a recursive call graph, and that graph perfectly mirrors the grammar of arithmetic expressions. 3 plus 4 * 2 parses to 11. 3 plus 4 * 2 parses to 14. Operator precedence falls out naturally from the grammar structure. Beat. Click. The mutual recursion call graph makes the dependency cycle explicit. Parse_expr calls parse_term, calls parse_factor, calls parse_expr for parentheses. Beat. Click. The state machine diagram shows another angle. State_even and state_odd alternate with each step, together implementing a parity machine through nothing but function calls. Important caveat. Python does not optimize mutual tail calls any more than it optimizes direct tail calls. For deep mutual recursion, say, on a deeply nested expression, you'll hit recursion error just as you would with direct recursion. The fix is the trampoline pattern, which we'll cover shortly. We saw with Fibonacci that overlapping subproblems, recomputing the same input multiple times, is the enemy of naive recursion. Memoization caches results so each unique input is computed exactly once, converting exponential time to polynomial. Click climbing stairs. How many distinct ways to reach step n taking 1 or 2 steps at a time? Base cases. 1 way to reach step 0, and 1 way to reach step 1. Otherwise, climb_stairs, n equals climb_stairs n1, plus climb_stairs n2, the exact Fibonacci recurrence. With @LRU_cache, this runs instantly for large n. Beat. Click. Longest common subsequence. The LCS of 2 strings has the classic memoize structure. If characters match, take 1 plus the LCS of the rest of both strings. If they don't, take the max of skipping from string 1, or skipping from string 2. 4 arguments, 2 reduction patterns, 1 cache entry per state, OM times n, states total. Beat. Click 0/1 knapsack. Given items with weights and values, what's the maximum value achievable within a capacity? State is n, capacity. Which items remain and remaining capacity? Each item is either skipped or taken, if it fits. Manual memo dictionary caches results. ON times W, states, O1 per state. Beat. Click. When should you use memoization versus tabulation? Memoization, top down, is simpler to write, and only computes the subproblems you actually need. Tabulation, bottom up, avoids recursion overhead, works with Python's recursion limit, and is usually faster in practice due to cache-friendly array access. Choose memoization for sparse subproblem graphs. Choose tabulation when you need most or all subproblems. Beat. Click the @LRU_cache and @cache decorators are all you need for most DP problems in Python. Cache from Python 3.9 is a simpler unbounded LRU cache. Use cache_clear to reset between test cases and cache_info to profile hit rates. A recursive call is tail recursive when it is the very last operation the function performs. No computation left to do after the call returns. In languages like Haskell, Scala, or Scheme, the compiler detects this pattern and replaces the call with a simple jump, reusing the current stack frame. No new frame means no stack growth. A tail recursive function can recurse a billion times in O1 stack space. ClickPython deliberately does not do this. Guido van Rossum's reasoning is explicit. Tail call optimization hides stack frames from tracebacks, making debugging harder. In Python, explicit is better than implicit. If you want iteration, write iteration. Glicko, how do we get the benefit of tail recursion in Python? The answer is trampolining. Instead of calling the next recursion directly, the function returns a thunk, a zero-argument lambda that represents the next call. The trampoline wrapper keeps calling the result as long as it's callable. The loop replaces the call stack. Beat. The trampoline decorator is the key. Wrap any function with it, and replace every tail recursive call with return lambda function, next underscore args. The decorator's while loop drives execution without growing the system stack. Fact underscore tramp, 1000, works fine. No recursion error. Beat. The same trampoline technique works for mutual recursion. Tr underscore even 10,000, and tr underscore odd alternate through 10,000 lambda steps on the heap, 0 stack frames. Beat. Continuation passing style is a formal version of this. Instead of returning a value, each function takes an explicit continuation, a callback, and passes its result forward to that continuation. CPS makes the data flow explicit. Combined with a trampoline, it supports deep computation in O1 stack. In practice, for most Python code, simply converting tail recursion to an explicit while loop with an accumulator is the clearest solution. Next, every recursive algorithm can be made iterative. For linear recursion, the conversion is an accumulator loop. For tree recursion and DFS, the conversion uses an explicit stack, a Python list that manually simulates what the call stack was doing automatically. Click tree in order traversal is the clearest example. The recursive version calls DFS, node.left, appends the node value, then calls DFS, node.right. The iterative version replaces the implicit call stack with an explicit one. Walk as far left as possible, pushing nodes onto the stack. When you can't go left, pop the stack, that's the node to process, then move to its right child. Same output, no recursion depth limit. Beat. Click graph DFS follows the same pattern. The recursive version visits the node, marks it, then recurses into each unvisited neighbor. The iterative version starts with stack equals start. In the loop, pop, skip if visited, mark, add to result, push all neighbors in reversed order. Reversed order preserves the same left to right traversal order as the recursive version. Beat. Click Tower of Hanoi iteratively. Encode each recursive call as a tuple, disks, source, destination via, on the stack. Pop a tuple. If one disk, record the move directly. Otherwise, push 3 new tuples. Move n-1 to via, move disk n to destination, move n-1 from via to destination. The stack drives the same sequence of operations the call stack would have. Beat. The conversion recipe is simple. Identify whether the recursion is linear or tree-shaped. Linear. Replace with an accumulator loop. The while condition mirrors the recursive condition. Tree-shaped. Use an explicit list as a stack. Push frames as tuples. Pop and process in the loop. The when to convert table. At depth greater than 1000, consider it. At depth greater than 10,000, it's mandatory. For performance-critical paths, iterative code is always faster, no function call overhead. Next, when you genuinely need deep recursion, Python gives you several tools, but each comes with trade-offs. Click SYS set recursion limit. N is the blunt instrument. The default is 1000. Each frame uses a few kilobytes of C stack space, so setting the limit to 1,000,000 frames might consume gigabytes of stack and crash the process with a seg fault, not a clean Python exception. Use it carefully and with a specific N in mind. Beat. Click S manager pattern, recursion underscore limit. N is the polite version. Raise the limit for a specific block of code, then restore the original limit on exit, even if an exception occurs. This prevents accidentally leaving a dangerously high limit active outside your controlled section. Beat. The generator recursion pattern sidesteps the C call stack entirely. Flatten underscore general uses yield from flatten underscore gen item for nested lists. Python generator frames live on the heap, not the C stack. A nesting depth of 1,000,000 levels is perfectly fine. You'll run out of heap memory before you hit any artificial limit. The comparison table is striking. Standard recursion maxes out at about 950 safe frames. An explicit stack or generator approach is limited only by available RAM. Beat. Click. The DFS underscore generator function shows the general pattern. Explicit stack is a list on the heap, yield for each visited node. Works on any tree or graph, handles arbitrary depth, and produces results lazily, only computing what the caller consumes. Beat. When choosing. For production code with potentially deep structure, prefer explicit stacks or generators. Reserve set recursion limit for when you have strong guarantees about input depth and need the simplest code. Next. 5 essential patterns appear over and over in recursive programming. Recognizing the pattern immediately tells you the solution structure. Click Pattern 1. Accumulate results in a list with backtracking. Find underscore all underscore paths explores all paths from start to end in a graph. The result list collects finished paths. The DFS function adds a neighbor to the current path, marks it visited, recurses, then removes it from both, the classic choose explore unchoose backtracking structure. Beat. Click Pattern 2. Pass indices, not slices. The bad underscore sum function creates a range by 1 on every call, a new list object, on copies, on squared total. The fast underscore sum version passes low and high indices. No allocation, constant time per call, on total. This is one of the most common sources of hidden quadratic behavior in recursive Python code. Beat. Click pattern 3. Return multiple values via tuple. Min_max finds the minimum and maximum of an array simultaneously in a single recursive pass. Returning a tuple of min-max avoids a second traversal. The divide and conquer structure computes LMIN, LMax, and RMIN, RMax from each half, then combines with a single min and max call. Beat. Click pattern 4. Generate a recursion for lazy output. Permutations_general yields permutations one at a time, rather than building the entire nen list in memory. When n is 10, and you only need the first 5 permutations, you avoid 99.9% of the computation. Yield from threads results through the call chain without blocking. Beat. Click pattern 5. Structural recursion on nested data. Count_leaves counts all non-dictionary values in an arbitrarily nested dictionary. Think JSON. Base case, if the current value is not a dict, it's a leaf, return 1. Recursive case, sum count_leaves, v, over all dictionary values. Works on any nesting depth, any dictionary shape. This pattern generalizes to any tree-shaped data structure. Next. Trees and graphs are where recursion truly shines. The recursive structure of a tree, every node is the root of its own subtree, maps perfectly onto recursive function calls. Each function handles exactly one node, and trusts recursion to handle its children. Click height, base case is null, return 0. Otherwise return 1 plus the max of the left and right subtree heights. This is the simplest possible tree recursion, and the foundation for many more complex ones. Beat. Click diameter. The diameter is the length of the longest path between any two nodes, which might not pass through the root. The trick. At each node compute the left depth and right depth. The path through this node has length L plus R. Update the global max. Return 1 plus the larger depth for the parent's calculation. 1 pass through the tree, on. Beat. Click has_path_sum. At a leaf node, check if its value equals the remaining target. Otherwise subtract the current node's value and recurse into both children. Return true if either path succeeds. Short-circuit evaluation means we stop as soon as one path succeeds. Beat. Click invert_tree, aka the infamous Google interview question, is beautifully one-lined with recursion. Swap left and right children, recursively invert both. Every node in the tree gets its children swapped in a single on pass. Beat. Click is_valid_bst, uses a technique that's easy to get wrong. Passing min and max bounds down the tree, rather than comparing just with the parent. For the right subtree, the lower bound is updated to the current node's value. For the left subtree, the upper bound is updated. This correctly handles cases where a grandchild violates the BST property relative to a grandparent. 1 pass. On. Beat. The key tree recursion patterns table is worth committing to memory. Height, size, sum, path accumulation, bound propagation, LCA split, and diameter tracking each have their canonical recursive form. Recognize the form, and the solution writes itself. Next, let's go through the mistakes that produce bugs or crashes in recursive Python code and their fixes. Click missing base case is the most obvious. Bad_sum calls itself forever until Python raises recursion error. Always add the termination condition before the recursive call. Beat. Click wrong base case, off by 1. Bad_fact returns 0 for n equals 0. Wrong. Factorial of 0 is 1, not 0. This propagates silently, giving bad_fact 5 equals 0 with no error message. The mathematical base case is 0 equals 1 equals 1. Always test factorial 0 and factorial 1 before trusting your implementation. Beat. Mutable default argument. Defining permutations, arranged by path equals, uses a single list object shared across all calls. The first call works. Subsequent calls find path already containing leftover data from the previous call. Always use path equals none, and assign inside the function. If path is none, path equals. Beat. Click on slices on every call. Sum_bad creates arranged by 1. Each call an on operation, so the total is on squared. Pass indices instead. Beat. Click forgetting to restore backtrack state for pathfinding. In DFS that finds all paths, you must remove the node from the visited set after recursing, otherwise later paths that should include that node will incorrectly find it blocked. Visited.remove node is the backtrack step for visited sets. Beat. Click on the positive side. Always handle the base case first. Use at LRU_cache for anything with overlapping subproblems. Pass indices not slices for array-based recursion. Prefer generators for large outputs. Convert to iterative before deploying recursion that could exceed depth 1000. And always test boundary inputs, 0, 1, and a known large case. Next. Analyzing recursive algorithms requires recurrence relations, equations that express the runtime of Tn in terms of T of smaller inputs. Solving these relations gives you the closed form big O. Click. The master theorem handles the most common divide and conquer recurrences. T of n equals A times Tn/B plus f of n, where A is the number of subproblems, B is the factor by which input size shrinks, and f of n is the combine cost. Compare fn against n raised to log base b of A. If f is smaller, root dominated, result is on caret log underscore ba. If equal, balanced, multiply by log n. If f is larger, leaf dominated, result is ofn. Beat. Click. The recurrence table maps beautifully onto algorithms. We know T of n equals Tn1 plus O1. Factorial, countdown, gives On. T of n equals Tm1 plus On. Insertion sorts inner shift, gives On squared. T of n equals T of n/2 plus O1. Binary search gives O log n. T of n equals 2, T of n/2 plus On. Merge sort gives On log n. T of n equals 2, Tn1 plus O1. Tower of Hanoi gives O2 caret n. T of n equals Tm1 plus Tn2. Naive Fibonacci gives On caret n, the golden ratio to the n. Beat. Space complexity of a recursive algorithm equals the recursion depth times the space per frame. Linear recursion to depth n, On space. Binary recursion having each call, O log n, depth, O log n space. Balanced tree recursion, O log n, depth, O log n space. Naive Fibonacci, On depth, despite making 2 caret n calls. The deepest call chain is n long. Beat. The substitution method gives you a tool for recurrences the master theorem doesn't cover. Unroll the recurrence by hand for several steps, spot the pattern, express T of n as a sum, evaluate the sum. T of n equals T of n1 plus n telescopes to 1 plus 2 plus 3 plus n, which is nn plus 1 / 2 On squared. This is exactly insertion sort. The recursion pattern taxonomy brings everything together. Click. Every recursive algorithm starts with a base case, the trivial answer, and a recursive case, the problem reduced. The recursive case branches into 5 shapes: linear reduction n to n-1 in On depth, binary reduction n to n/2 in O log n depth, divide and conquer splitting into 2 halves in On log n total, backtracking exploring choices with pruning and exponential best prune time, and memoized DP where overlapping subproblems are cached for polynomial total. Click the quick decision guide, overlapping subproblems, reach for at LRU_cache. Tree or graph traversal. Recursion is natural. Convert to iterative stack if depth exceeds 1000. All combinations or permutations, backtracking. Having the input, divide and conquer. Deep recursion in production, explicit stack or trampoline. Streaming large output, generator with yield from. Beat. Click the Python toolkit, at cache for memoization. Trampoline decorator for deep tail recursion. The backtracking template, make choice, recurse, undo choice, for combinatorial search. Yield from, for lazy recursive generators. The explicit DFS function, with a stack for unlimited depth. Beat. The complexity quick reference confirms. Linear recursion On time and space. Binary O log n. Merge divide and conquer, On log n time On space. Backtracking OB caret D, with pruning, memoized DPO states. Beat. Recursion is fundamentally about asking the right question at the right scale. When you see a problem that breaks naturally into smaller versions of itself, recursion expresses that insight directly in code. Master these patterns and you'll recognize them instantly, in interview problems, in production systems, and everywhere in between. Next. That's recursion, from the 3 laws on the call stack all the way through backtracking, memoization, trampolining, and the practical patterns you'll reach for every day. The code for every example shown is linked in the description. If this helped, like and subscribe. The next video continues the algorithm series. See you there.